Hello again. So now we will move on into Bayes rule. That is going to be the core of the course. So we need to understand it very well. And you will see that it's very simple and very elegant. So quick recap, we have the condition probability that has this formula and also these two properties. And we can understand it via cross tables with marginals and conditioned frequencies and also probabilities. Okay, so now we will have this simple development to apply to Bayes rule, so just follow me. Okay, so we have this conditional probability formula, and we can start operating with that. For example, we can multiply the probability of B to both members, so we can simplify these two to get something that we already knew. The probability of A and B happening at the same time is the conditional probability of A given B multiplying the probability of B. Now we can apply this to the condition probability of B given A, the inverse condition probability. So we get the probability of B given A multiplying the probability of A is equal to the probability of B and A happening at the same time. Now that we know that the probability of A given B, A and B is the probability of B and A, because switching the places in intersection does not have any impact on the concept because it's basically a product. Okay, so now we can substitute and get probability of A given B multiplying probability of B is equal, because it's the probability of A and B, to the probability of B given A multiplying the probability of A, because it's probability of B and A happening at the same time. We can move the probability of B over the second member, so we have the Bayes theorem. That is, probability of A given B is the inverse conditional probability multiplying by one of the marginals, the probability of A, and divided by the other marginal. Okay, so this is essentially the Bayes rule. Conditional probability of something can be calculated with the inverse conditional probability and the marginals of both members using this simple formula. So the main advantage of this is that we can obtain inaccessible condition probabilities using known condition probabilities and their marginals. So this is the basis for Bayesian inference that we'll cover on later sessions. Okay, so if we also recover the cross tables and start applying Bayes rule, remember that we can get to any joint or any combined intersection of probability of two things happening at the same time if we just turn them into the condition probabilities multiplying their respective marginal. Okay, so given that in binary variables we have their complementaries, we can get all of the four possibilities, and applying Bayes rule, we know that the probability of A given B multiplying the probability of B is equal to the inverse probability B given A and multiplying probability of A. We can do that for all of the four combinations, and we get two equal cross tables. Okay, so this is very useful. Why? Because we can generalize it to an indeterminate number of values. So we have this, and two variables, A and B, rows and columns, and we have an undetermined number of values for A and for B. We have the marginals that we would just call the probability of A having any value and B having any value. However, the cells are going to have this expression that is going to be the probability of A and B having any possible value of each one of them, that is going to be equal of the condition probability of A given B in this pair of values multiplied by the marginal of B. But also the probability of B given A in a pair of values multiplied by the marginal of A. So now we have something interesting. We can also get to the total or marginal of each of the variables. So if we have a discrete variable, it's going to be pretty easy. We just need to sum the values. For example, sum of all of the rows, row by row. and we will have the marginal probabilities of each of the values of A. However, we will have a continuous variable. We just need to make an integral. That is tougher, but we just have an abstract solution. So that is very nice. Okay, so let's have a quick example. Let's say that we need to, or we want to study a rare disease in patients. We know that only 1% of the population is infected. Therefore, we have a binary variable that has values 0 and 1. 0 is healthy, 1 is infected. And the probability of being infected, that is having a 1, is 0.001, 1%. We have a test with 99% hits and 5% type 1 error. So we have also a binary variable that is having a test that is 0 negative, 1 positive. The probability of having a hit, that is having a positive test, given you are infected, is 0.99. And the probability of type 1 error is having a positive test given you are healthy, and that is 0.05. We select a random person from the population and comes out a positive test. Which is the probability of having a disease? Okay, so this is interesting because we need Bayes' rule. The objective is not having a positive test given it's infected. It's the other way around. We want the probability of being infected given the positive test has already occurred. Okay? So the intuitive answer would be just having the complementary of being infected, that is 0.001. 1 minus this value is 0.999. But this is basically wrong. We need to be exhaustive. So the exhaustive answer is to build the whole cross table and then have a value. So we have being infected or healthy, having a positive or a negative test, and we have our 4 cells and our marginals. Remember that these 4 cells are expressed as the condition probabilities of test given infected or healthy, multiplying by the marginal of infected or healthy, the respective marginal, just to be comfortable with the information that we already know. Okay, so we just need to start substituting. We know that the probability of being infected is 1%, therefore the marginal for being infected is 0.001, and the complementary, being healthy, is 0.999. Okay, now we know that the condition probability of having a positive test given it's infected is 0.99. Okay, so if we want to get to the intersection, that is having a positive test and being infected at the same time, we have to get this condition probability that we already know, 0.99, and multiply it by the marginal of being infected, that is 0.001. Therefore, we just need to do this simple operation to get to this probability. We can do exactly the same with having a positive test. Having a positive test given you are healthy, that is 0.05, the type 1 error, and with this simple operation, 0.05 multiplying by the marginal of being healthy, that is 0.999, we just get to this other probability. Okay, now we also know that we just need to know the condition probabilities of having a negative test given you are healthy or given you are infected, multiplied by their marginals that we already know to get to these other 2. Okay, so moving on, we just substitute, and we already know that the probability of having a positive test given you are healthy is 0.99, and therefore having a negative test given you are infected, that is the same condition, therefore being infected is 1, is the sample space, so having a positive is 0.99, having a negative should be everything that is not having a positive, therefore it's complementary. 1 minus 0.99 is 0.01. We can do the same for the other. The condition probability of being having a positive test given you are healthy is 0.05. Therefore, having a negative test in the same condition should be its complementary, that is 0.95. So we have 0.01 multiplying for the conditional, the marginal, excuse me, and also 0.95 multiplying for the respective marginal. Okay, so we already have these 4 numbers. And now we need to complete the table. We already remain with the marginals of having a positive test or a negative test. So because we have a binary variable, it's pretty simple. We just need to sum the values. We need to make the sum of having a positive test in any value of the disease and multiply it by their marginals. We already have those numbers, that is 0.00099 and 0.0499, and the sum is 0.05089. We already can apply that to the probability of having a negative, that is the same operation but with different numbers because it's a different row, 0.00001 and 0.9491, that is these two values, this value and this value. And we have 0.94911, that is this marginal. So we have the complete cross table. Now we can get to our goal, that is having the probability of being infected given you have a positive test. Okay, so we need to focus on the row of getting a positive test and apply Bayes' rule. So the probability of being infected given you have a positive test should be the probability of that we already knew, having a positive test given you are infected multiplied by the probability of getting infected. We already know this number, 0.00099. And we need to divide it by the probability of getting a positive, that is the sum of the other two values. We already know this number, 0.5089. That we have is 0.0019. So the probability of being infected given you have a positive test is very small. You have a 1.9% chance of being infected with this rare disease if you have a positive test, in spite of having a really high percentage of hits. Why is this? Basically because the probability of infection is very low and we have a 5% type 1 error. If we have to be very precise with a very rare thing to happen, we need a very low type 1 error and a very low type 2 error, therefore a lot of hits and a lot of correct rejections. So as you can see here, simple, elegant, and fascinating regarding Bayes' rule.